All right, today we've got 8.1. We're doing function operations, so starting a new chapter with functions. Our objectives are to find the sum, difference, product, and quotient of functions, so a lot, and it says find the composition of functions. So first of all, let's look at these function operations, okay, this table. So in addition, we can say f plus g of x. So this is function f plus function g of x, whatever our x value is. So that's the same thing of saying, okay, well, if we find our function of x, like f of x, and we find the g of x, and then we add those together. So we could separate our equation. In subtraction, it's the same thing, right? F minus g of x. So we're going to take our f of x equation, we're going to plug x in for that and solve it, and then we're going to plug x in for our g of x equation and solve it, and then we can subtract those. In multiplication, if we have fg of x, it's just multiplying the function f of x times g of x. And here, when we have division, f divided by g of x, same thing, we're splitting this up. We're going to do f of x divided by the g of x. Obviously, our g of x, we do not want it to equal 0. Otherwise, it's impossible, right? We can't do anything divided by 0. Okay, so let me move this up a little bit so we can see our chart, or the rest of our things there. Okay, so functions are excellent tools for creating models in science, engineering, technology, and economics. Okay, the sum, difference, product, and quotient of functions are defined by the following function operations, which are right there. Okay. The domain, so we're talking about domain, of the resulting function is the intersection of the domains of the two functions. Okay, so where do they intersect? Okay, so the domain of the resulting function is the intersection of the domains of the two functions. The domain of the resulting function may also be limited by the fact that the division by zeros is undefined, which is happening here, right? Our domain is limited. So functions can be thought of as machines, where each machine performs a specific function. So like addition, subtraction, whatever. The addition of two functions can be illustrated as the sum of the outputs of two different function machines. So what that's saying is here, if we have this function, okay, it's f of x, we're going to take the, to do this, we're going to take our x value and add 1 and then square that quantity. So if we put a 4 in this machine, okay, it's going to put 4 in for x. So this is going to be 4 plus 1. And then we square that, so that's 5 squared. So we get a 25 out. If we put a function, so then we have the g of x function. So it's going to take the x and subtract 2. So in this g of x machine, if we put a 4 in, that's going to be 4 minus 2, which gives us 2. All right, so if we're taking this, okay, functions can be thought of as machines, where each machine performs the function. So each machine did its function. And then the addition of two functions can be illustrated as the sum of the outputs. So this is the addition of these two functions. So f of 4 plus g of 4 equals the 27. So that's what I'm taking the 25 I got from the f of x function machine, adding it to the 2 that I got from the g of x function machine, and I get 27. Okay, so we're just combining functions. Okay, an operation with two functions can be written as one equivalent function. So that's kind of what we're working on today. An operation with two functions, if it has two functions, can be written as one equivalent function. So in example 1, we have f of x equals x, the quantity x plus 1 squared, and g of x equals x minus 2. Okay, so those are those functions that we just saw. It says write the function rule representing the result of each function operation. Okay, so let me actually move up here. Let's take a minute and clear this so I have some room to work. Okay. I swear I focused this, but it seems rather out of focus. There we go. That does look better. All right, so if we have this equation, for the first one, we have the quantity f plus g of x. Well, we just said up above in the table that that's equal to our f of x plus our g of x. This one's already really done for you. Okay. So our f of x is the x plus 1. So this is going to be the quantity x plus 1 squared plus our g of x is the quantity x minus 2. Okay, so we're going to have to do some math here, right? We're going to have to distribute this. So we have x plus 1 times x plus 1. So x times x is x squared. X times 1 is plus x plus 1. And then we still have plus the quantity x minus 2. Right, so we're going to put in plus. Then we have a plus sign here, so we have to think, do I distribute? Like, is anything going to change when I distribute this? No. So it's just going to be plus x minus 2. All right. So then we have x squared, because we don't have anything else like that, plus x plus x plus x. Well, that's 3x, right? So plus 3x. And then we have plus 1 minus 2. So that's minus 1. Let me change up my colors a little bit. For the next one, I have the quantity f minus g of x. Well, that's equal to f of x function minus our g of x function. Okay, so our f of x is still the quantity x plus 1 squared minus, this time, our quantity x minus 2. All right, well, I already did all this math here, right, to square that, so I know that this x plus 1 squared is equal to x squared minus, or plus, pardon me, 2x plus 1. So instead of having to do all that work again, I'm just going to write that down there. So we've got x squared plus 2x plus 1. And then we have a minus, so we have to distribute that. Now, it's going to change stuff, right? A negative times x is going to make it minus x. A negative times a negative is going to make it plus 2. All right, and then we simplify. We have 1x squared. We have a positive 2x and a minus x. So that's going to be plus x. A positive 1 plus 2, so plus 3. X squared plus x plus 3. All right, so hopefully so far you're like, oh, this isn't bad. We can rock this. We're going to look at multiplication and division next. Okay, so we have C, the quantity f times g of x. So that's just f of x, right? Times, I'm going to use my little dot, the g of x. So this is f of x is that quantity, x plus 1 squared, times g of x is that quantity, x minus 2. All right, x plus 1 squared we know is equal to x squared plus 2x plus 1. Okay, and that's being multiplied by the quantity x minus 2. So I'm going to have to do some distributing here. So x squared times x is x cubed. X squared times negative 2 is negative 2x. All right, then I'm going to do 2x times x. That's a positive 2x squared. 2x times negative 2 is going to be negative 4x. Then I'm going to do 1 times x is a positive x. 1 times negative 2 is negative 2. Okay, so now I have an x cubed. Sorry, I thought I changed my color there, but I didn't. And I have a 2x squared. All right, and then I've got negative 2x minus 4x plus x. So negative 2 minus negative 2x minus 2x is going to be negative 6x. Plus x is negative 5. Oh, wait, did I skip something? Hold on. I made a mistake. Yes, I did. Ha! You all probably found it before I did. So this one, x squared times x, this should have been negative 2x squared. Okay, which would have changed my, I was like, wait a minute, something here is off. So let me go back this. So I have negative 2x squared plus 2x squared, so those cancel. There we go. Then I have a negative 4x plus x. That's going to give me a negative 3x or minus 3x. All right. And then I have minus 2. So there is my simplified answer on that one. Obviously, you need to be careful when you're distributing or you'll screw up like I did. You don't want to have to do that. All right. Then for D, we have f divided by g of x. So this is just equal to our f of x divided by our g of x. All right, so our f of x is that equation, that quantity, x plus 1 squared, divided by the quantity x minus 2. Okay. This is one of those cases where it's actually easier to not FOIL this. Okay, we could just write it out like x plus 1 times x plus 1 divided by x minus 2. And look at that and see if we have any like terms, right? So we're looking for like terms. And I'm going to write that, and then I'm going to put a question mark and say nope or none. So this one is already simplified. Like we can't simplify it further. But because there are no like terms, but we do need to set a limit. Okay? Because our denominator, check out our denominator, right? We have x minus 2, so we must set a limit because our denominator does not equal 0. We never want that denominator to be 0. So what do we need to say for our limit? So essentially, what can x not be? X cannot equal what? Perfect. X cannot equal 2. Okay, because if it did, if we had x as 2, we would have 2 minus 2 equals 0. Our denominator would be 0. That cannot happen. So our answer, this is our answer, and we have to set the limit at x is not equal to 2 as part of that. So if you can't simplify it, always check to see if you can set a limit for it. All right. Okay, then we have the composition of two functions, f and g, is denoted f of g. So we've got this little bitty O up there. Kind of looks like a degree sign. All right. So, and this is defined as f of g of x, which is f of g of x. There's another way, which is read f of g of x. Whew. All right. So, expressing this f of g of x, when we have the like degree symbol, as f parentheses g parentheses x, is helpful when evaluating a composition of functions for a given value of x. So first, evaluate the inner function, and which is g of x here, right? It's the inner function. Then use the resulting value. Okay, so then we're going to use the resulting value to evaluate f of x. Okay, so essentially what it's doing, okay, so the g of x is coming first. So we put a number in and we evaluate it and we get that number out. We got a new number, right? We put 5 in, we got 11 out. So now we put 11 in this new function to get our final answer. Okay, so we're doing the inner function first, and then we do the put that into the remaining function. But this is key. We do the inner function first. So order doesn't necessarily matter. Example 2, we're going to evaluate each expression when f of x equals x squared minus 3 and g of x equals 2x plus 1. Okay, in this case, we have f of g of x. Our x is negative 2. So we're going to write this as f of g of x. And we're going to evaluate that inner function first. So we're going to do g of x for negative 2. We're going to put negative 2 in for that x. Okay, so let's do that. So we've got our g of x is 2x plus 1. So we're going to do 2x plus 1. We're going to put a negative 2 in there. So let me just go ahead and do that. So I'm going to do 2 times negative 2 plus 1. 2 times negative 2 is negative 4 plus 1 is 3. Negative 3, pardon me. All right, so this is what I got for my g of x. Now I'm going to plug this into my remaining function. All right, so in that one, so my f of g, no, ah, keep thinking I'm clicking and I'm not. So for my next one, f of, like you might call this f of x even at this point. I'm not for sure. Okay, but we're going to go ahead and call it f of g of x because we're putting our because now it makes sense, right? We're taking this is what we got for our g of x and we're going to put it in there in this one because it's f of g of x. So when we have that equation, f of x equals x squared minus 3. Okay, our x this time is negative 3. So we've got this x squared minus 3. Okay, so I'm going to put my negative 3 in there. So this is going to be negative 3 squared minus 3. Negative 3 squared is 9. 9 minus 3 is 6. So my f of g of x equals 6. Okay, but here's the other thing and actually how we write this. Because we know our x value. So this should say f of g of, hopefully my pen color changed, it did, f of g of negative 2 equals 6. Okay, because I plugged in the negative 2. Because I'm going to solve it again, but I'm going to do it with b, and I'm going to use 3 for my x. So this is going to be f of g of 3. Okay. All right, so we're solving the inner equation first. Okay, so we're going to do our g of 3 first. So g of 3 is going to be 2x, so 2 times 3 plus 1. Well, 2 times 3 is 6. 6 plus 1 is 7. And then we're going to do our f of g of 3. Okay, well, my g of 3 equals 7. So I'm going to plug 7 into this equation for my g of 3. So my f is, remember, it's x squared minus 3, but I'm plugging a 7 in. So this is going to be 7 squared minus 3. So 49 minus 3 is 46. So my f of g of 3 equals 46. All right, C. This time we've changed the order. We're going to do g of f of 3. So we're going to do g of f of 3. All right, so we're going to solve the inner one first. So I'm going to do f of 3. Well, my f is x squared minus 3. So let's see. So we've got f of 3 equals x squared minus 3. So I'm putting in 3. So this is going to be 3 squared minus 3. 3 squared is 9, minus 3 is 6. Okay. So now I'm going to solve my g of f of 3. Okay, my g of x is 2x plus 1. But remember, my f of 3 value that I got out right here, right? I did the work for f of 3 and I got out a 6. So now I'm plugging that in. So this is going to be equal to 2 times 6 plus 1. 2 times 6 is 12, plus 1 is 13. So g of f of 3 equals 13. So here is a good question. Does the commutative property apply? Like if we look at this problem where we did f of g of 3, and here when we did g of f of 3. We both had 3 as our x. But did we come out with the same answer? No, right? 1 equaled 46 and 1 equaled 13, which means that the commutative property does not apply to functions. It does not apply. Okay, let's move on down here to example 3. If f of x equals x squared minus 3 and g of x equals 2x plus 1, write a single function rule representing each composition. Okay, so that may seem a little weird, like what are they asking us to do? We just want to write a simplified version. Okay, so if this is, remember this is equal to f of g of x. Okay, so when it says write a single function rule, okay, we're just going to walk through and we're going to leave the numbers. We're not going to, or we're going to leave the variables. We're not going to put numbers in. So let's think about this. Let's see, our f of x, okay, so let's see, our f of x, because that's what we're starting with here. Our f of x equals x squared minus 3. Okay, and we're supposed to do the inner function, right, solve the inner function and place that into kind of like what remains, the f, right, because we take this f of x and we say, oh, this is f of g of x. Okay, so what's that saying is we're gonna, to get this, we're gonna take this x squared minus 3 and we're gonna put g of x in for x. So our g of x is the 2x plus 1. So here in this quantity, that x squared, I'm gonna say, oh, well, this is 2x plus 1 squared minus 3. So all I did, again, is like, as I started, my outermost function is the f of x equals x squared minus 3. I'm taking the g of x, okay, quantity, and I'm inserting it in place of my x in both parts of my equation. Now I actually need to simplify this. Okay, so if I do some work over here, right, 2x plus 1 squared, so 2x plus 1, 2x times 2x is going to give me 4x squared plus 2x plus 2x plus 1. So this is 4x squared plus 4x plus 1. Okay, so let's bring that back over here. So now I've got 4x squared plus 4x plus 1. And then we don't want to forget our minus 3. All right, so we can simplify this. Can't simplify my x squareds. I don't have any other x's, so plus 4x. However, I have plus 1 minus 3. Well, that's equal to minus 2. So f of g of x equals 4x squared plus 4x minus 2. If we just leave it as a single function rule. Okay, so we combine these two functions into one single function is what we're doing there. All right, we're going to do the same thing with the g of x over here, or g of f of x. Oh, doggone. So we've got this is equal to g of f of x. Okay, but our outermost one is g of x. So I'm going to start with that. So I've got g of x equals my 2x plus 1. Okay, but I want to insert the f of x, right? I want to insert my f of x in there because it's g of f of x. So to do that, I've got 2 times x, which is x squared minus 3. So times the quantity x squared minus 3 plus 1. All right, so then I'm going to distribute. 2 times x squared is 2x squared. 2 times negative 3 is negative 6 plus 1, which gives me 2x squared minus 5. And that is my g of f of x value. Awesome. So that is how you write it again as a single function rule. Okay, so again, we could look at this. We can look at these two equations. Does the commutative property apply? Right? F of g of x and g of f of x. Did I come out with the same equation? Definitely not. So the commutative property does not apply to functions. Definitely does not. All right. This is a long lesson today. We'll spend a couple days in class working on these things. Example 4. If we have, it says if f equals the set -2, -1, 0, 1, 2, 3, and g equals the set 1, 2, 2, 0, and 3, -2. Find each composite function and state its domain. Whew, man, that's a lot, isn't it? Okay, so first of all, we have f of g. Well, this is equal to our f of g of x, we know. Okay. So when we're looking at this, we have our f values, we have our g values. Okay. So if we have f of g of 1, let's break that down a little bit. So let's see, I have f of g of 1. Okay. Then think about what we've been doing. We've been putting our g of x, right, in here when we have a 1. Okay, so what is our g of 1? Okay, the reason I picked a 1 was because I had this. So when I put f of g of 1 in, when I put the 1 in, then I get out a 2. Okay, so then that's going to make this f of 2 because I put 2 in for this. So if I put 1 in, I get 2 out. Well, then I have to come back to my f's over here and see where did I put a 2 in for my first value. Oh, there's my x value for the 2, and I get a 3 out there. That might seem a little wonky, so let's walk through that again. Okay, we'll use a different one. So if we do f of g, okay, I use the 1. Let's put my x value in there. Let's put a 2 in. Okay, so if I put a 2 in for my x, what do I get out? What's my y value? Again, I'm just looking at my g's. I want a g of 2. When I put a 2 in for x, I get a 0 out. So that means I'm going to have f of 0. Okay, so now I come over here and look at my f's. Do I have an x value of 0? I do, it's right here. When I put a 0 in for x, I get a 1 out. So f of g of 2 is 1. Let's do another one. So I'm going to change this to f of g to f of g. Okay, my next one is a 3, so I'm going to put a 3 in for g. When I put a 3 in for my x value, I get out a -2. So I've done my g of work. So now I'm going to do f of -2. If I put a -2 in for my f value, or for the x in my f function, I get a -1 out. So my f of g of 3 is equal to -1. So then it said I was supposed to find each composite function and state its domain. All right, so let's do that. Let's look at the domain. The domain here is, oh, hold on. Find each composite function. Let me actually list all these. Let me take a step back, not a highlighter. Okay, so here, my f of g here, Okay, let's list that out in set notation first. Okay, let's find each composite function. Yes, okay, so let's find the composite function. My f of g, if I put a 1 in, I got a 3 out. So my set notation, I'd have 1, 3. I put 2 in, I got 1 out. So my next ordered pair is 2, 1. My last ordered pair is 3, negative 1. And so my domain, remember my domain is my x or y values. Good, is my x values. So my domain here is 1, 2, 3. I just list my x values from that set notation. Okay, we're going to give this a go again on the g of f over here. All right, so this time it's g of f of x. So let me erase all these markings I made the first round through. Okay, so this means we're going to do g of f of x. Well, what's our first x value in my f's? Negative 2, right? So g of f of negative 2. So when I put negative 2 in for x, I get negative 1 out. So now I've got g of negative 1. Okay, so do I have a negative 1 over here for g? G of 1, g of 2. I don't have a g of negative 1, so this is not defined. Because I don't have a negative 1 for an x value in my g function. Okay, so we'll try the next one. G of f of, okay, so if I go back to my f's, my next one up is 0. So I'm going to put a 0 in. When I put a 0 in for x in function f, I get a 1 out. So that's going to, now I'm going to put a 1 in for my g. So I go to my g function, I do have a 1. When I put 1 in, I get 2 out. All right, let's see, g of f of 2. So I'm going to put a 2 in. When I put a 2 in my f function, I get a 3 out. So this is going to be g of 3 then. Okay, if I go to my g function, do I have a 3 for an x value? I do. When I put the 3 in, I get negative 2 out. Okay, so my g of f, then I need to list my set for each one. So the first one, it's not defined. I don't list anything. Here, I have 0 for my f of x, my first x. I put a 0 in, and at the very end, I got a 2 out. So 0, 2 is my first ordered pair, and then 2, negative 2 is my second ordered pair, which makes my domain set 0 and 2, because my domain is my x values. All right. On to the next sheet, number 5. Like I said, we have a long thing to start this section off here. Giving you lots of practice and information. Okay, so in example 5, if we're given the real number function f of x equals 1 over x squared and g of x equals the square root of x minus 3, write the function rule for f of g and state its domain. Whew, okay. So now we're going back to last chapter and using these radical and exponential equations. All right, so we're writing a rule for f of g. Okay, so f of g, okay, equals f of g of x. Okay, so this is going to equal. Sometimes I find it helpful to write my f of x. Okay, or to write, like, put my g of x in there. So this is f of g of x. So I'm going to take this g of x part and I'm going to write it in there. So I'm going to find the function of the square root of x minus 3. And then, now that I know what my x equals, Okay, then I take and put x where it belongs here. Okay, so this is my x value, right? This is supposed to be my x. Maybe I don't write that. But this is f of x. So if I'm just looking at this, so this is going to be 1 over my x is the square root of x minus 3, and then I have to square it. And then that doesn't look quite so ugly, right? Another way to think about it, let me change this. So the other way you can think about it is like I've got, all right, my f of x equals 1 over x squared. And so I've got to put my g of x, right? My g of x, let's see, my g of x has to go in here, which means my g of x formula is going to go in there, right? If g of x is going here, then, or maybe another way I should write it, if g of x is going in place of x, then here needs to be the square root of x minus 3. Either way, you're going to end up with f of g of x equals 1 over the quantity, the square root of x minus 3, squared. Okay, so either of those is the same. Doesn't matter which way you think about getting there, okay, because this is an or. You can think about it either way. But we do need to finish it, so let's go ahead and finish it. So the square root of x minus 3 squared, that's awesome, is 1 over x minus 3. Okay, I can't really do anything else, so this is it simplified. However, I have a denominator, so I need to limit this. So what can x not equal? Because I don't want my denominator to be equal to 0. Remember, our denominator cannot equal 0. Cannot equal 0. So x cannot be good, a positive 3. That's part of it. Okay. Then we have to state its domain. Let's state its domain. All right, when we're looking for the domain, we need to look at the inner function. Okay, so when we're looking, this g of x is our inner function. So what's the domain of our inner function? So let's look at the domain of g of x. Okay, if g of x g of x equals the square root of x minus 3. What's the domain of that? So the domain of g of x is going to be x such that x what? What does x have to be? Okay, well, in order for us to have a square root, right, it has to be greater than 3. Or could it be, right, because then 3 minus 3 would be 0. Could it be, or let's see, 4 minus 3 would give us 1, and we could have a square root of 1, which is a real number. Could it be 0? 0 minus 3 is 0, or is, sorry, could it be equal to 3? Oh my gosh. Okay. Could it be equal to 3? So if we put a 3 in here, 3 minus 3 is 0. The square root of 0 is 0. So yes, here the domain could be, of g of x, could be x such that x is greater than or equal to 3. Now, we want to use that. Okay, so again, let me maybe put the because. Do you need a because statement? Right? Because the square root of 3 minus 3 would be the square root of 0, which is 0. So a real number. That's fine. So now we want to look at the domain of our function, of our composite function. Okay, so we want to look at the domain of our f of g. Okay, so it is x such that x. All right, now here, the way to think about it, so we needed to find our inner functions domain so that we could find our composite function domain. Because the domain of the composite function is the, let's see, how do I want to say this? Okay, so the domain of the composite function is the domain of the inner function, the one we just did, but we have to take away any values that would cause the composite function to be undefined. Okay, so because we said here, we limited this and said, okay, x cannot be 3, this domain no longer works because this domain said that it was x such that x was greater than or equal to 3. We limited it and said x cannot be 3. So our domain here is x is greater than 3. We're having to get rid of the negative. So again, if we kind of think about this, all right, it would be because if we had 1 over the square root of 3 minus 3, that would equal 1 over the square root of 0, which would equal 1 over 0. This is undefined. So we can't have we can't have x being equal to 0 here. So our domain for the composite function is there. But we have to find the inner function's domain, and then we use it and see if there's anything else we need to take out for the composite function. All right, we're going to actually stop there on this. We're not going to worry about the word problem because it's just some practice using it, which it is helpful. We might do it in class, but we're going to stop there for today because that was a lot of notes, and I will see you in class.